Welcome back. This is section 26.6 on magnetic dipoles. In the book, there's example 26.3, and I didn't cover it in a video lecture. You might want to look over it to see an example of the Biot-Savart law. But the results, well, what example 26.3 is about is a loop, a circular loop with a current. And it asks to find the magnetic field at an arbitrary point P on the axis of this circular loop of radius A that carries the current I. You see the setup right here. The point P is some distance x away. There's the current in the loop. And the result of example 26.3 is that the magnetic field right there along the axis is pointing away from it, so along the axis. And here's the result. The magnetic field is mu naught, so remember that's the permeability constant, times the current, times the radius squared, over 2 times the 3/2 power of x squared plus a squared. And I want to consider the result if we get far away from the loop, where x is much, much greater than a. So you take that limit as x is much, much greater than a, and the denominator just becomes 2x cubed. Now I'm going to multiply the top and bottom by pi, so multiply by pi over pi, and that gives mu naught I pi a squared divided by 2 pi x cubed. And the reason I did that, inserting that pi in there in the numerator, is it allows us to put this magnetic field in terms of the area of the loop. So here we have, I've set off in parentheses pi times little a squared, or pi times the radius squared, and that becomes the area of the loop. And what we're going to see is that this has ramifications for any current loop. It doesn't have to be a circular loop, but this is the magnetic field, mu naught I times the area of the loop over 2 pi and the cube of the distance from the loop, as long as we're looking along the axis. So there it is again, magnetic field is mu naught I a over 2 pi x cubed. And we define mu, so not mu naught, but just mu as the magnetic dipole moment of a loop. And the magnetic dipole moment is the current going around that loop times the area of the loop. And I want to compare this with the electric dipole moment. We looked at that back in chapter 20. When you have electric dipoles, so remember that means a positive and a negative charge, and they're equal and opposite to each other. We defined the electric dipole moment as the charge times the distance between them, or charge times separation. And the electric field from that was 2 times k, the Coulomb constant, times the electric dipole moment over x cubed. And I'm going to replace that Coulomb constant k with the more universal epsilon naught. And so that becomes p over 2 pi epsilon naught x cubed, because remember k is 1 over 4 pi epsilon naught. So when we looked at the electric field along the axis from an electric dipole, we got p, or the electric dipole moment, over 2 pi epsilon naught x cubed. And now compare that with the magnetic field from a loop, and that's mu naught mu over 2 pi x cubed. Now compare those. The mu naught over 2 pi versus the 1 over 2 pi epsilon naught with the electric field, those are just constants. And when we separate away those constants, we're left with, for the magnetic field, mu over x cubed, and for the electric field, p over x cubed. So you can see the similarities between those. So let's think about this useful concept called the magnetic dipole moment. And there it is, mu, and it's actually a vector. And again, don't confuse this with the constant, the permeability constant, mu naught. So this is mu that relates to a loop with a current going through it. And there it is. You can see the loop, and its dipole moment is mu. Now it's a vector, it faces perpendicularly away from, or perpendicularly from the face of the loop. And the direction of it, you have a 50-50 guess. If it's pointing perpendicularly away, it can either be going up or down in that picture. But what we're going to do is our right hand rule, where we take our right hand and curl our fingers in the direction of current. And your thumb, if it's opposing away from the hand, your thumb should point in the direction of the dipole moment. Now, there might be multiple loops. So let's say if there are 5 loops, we'll say n equals 5. So the effective current then is n times I. If it's a current of 1 ampere and there are 5 loops going around, then effectively, for purposes of the dipole moment, this is a current of 5 times 1 ampere, or 5 amperes. So if we allow for that there might be multiple loops, we can say that the magnetic dipole moment vector, mu, is n times I times A. Now you look at the loop at the top of the page, and I've only drawn one little vector, so the dipole moment, and that comes from on the previous page and from example 26.3, where we found the magnetic field that is along the axis. Well, let's think about that magnetic field, and we're going to zoom out from the loop. The magnetic field looks like this picture on the left. Certainly we have what example 26.3 led us to, that was just finding the magnetic field along the axis. But if we zoom out even more, we see that the magnetic field looks like this. Now, all along the loop, you can find the direction of the magnetic field around the current by using the right-hand rule, where you grab the wire with your right hand, your thumb points in the direction of current, and your fingers curl around the wire. Your fingers show the direction of the magnetic field. Well, here's what it looks like, the magnetic field from a current loop. And it looks a lot like an electric dipole, the electric field lines. You can see the similarities in the shape. Now, magnetic field lines do not begin or end. Like an electric field, the lines point, they go between the point charges. So you think an electric field, just imagine a dipole. The electric field lines just start at the positive charge and they end at the negative charge. But magnetic field lines do not begin or end. They loop around. They form closed loops encircling moving charges, which are their source. Now, the planet Earth has a magnetic field, and we can think of the Earth like this. We know it has magnetic field, and so I've drawn it before like this, going around from North Pole to South Pole, or South Pole to North Pole, depending on what you call those poles. And you can think of the Earth as being one big magnet, and it's got its magnetic dipole moments. There's mu of the entire planet, and it's pointing towards what we call the South Pole, but remember that is magnetic north. I also want you to note that the rotation axis is different from the magnetic axis on the Earth. So the Earth's magnetic poles aren't exactly on its rotation axis. And in fact, the magnetic poles of the Earth are just floating around, moving around a bit, and they move several miles per year. Now, the source of the magnetic field is that there are currents of charged particles inside the Earth, in the core, and those streams, currents of charged particles, whenever you have charged particles moving, remember, each charged particle in motion has an electric field. Well, you've got these large currents, these streams of electrically charged particles, and they are moving around in the Earth, and that's the source of the magnetic field. I want to think about the torque on a magnetic dipole. Now, a magnetic dipole in a magnetic field experiences a torque. In chapter 20, when we were talking about electric dipoles, in a uniform electric field that we saw that it experiences, an electric dipole experiences a torque that's equal to the cross product of the electric dipole and the electric field. And you can go back to chapter 20 to review that. But I want to look for now, how is a magnetic dipole affected? How is it torqued in a magnetic field? And I want to think about this. Here you have in the picture a wire loop with a current going through it. You can see that current that I've drawn going around in the counterclockwise direction. And we have a magnetic field that is pointing upwards. So what I've drawn in the purple right there, magnetic field pointing upwards. And let's give this loop, a rectangular loop, some dimensions. Let's give it a height of b and a length of a. And I want to think about how it is being forced. I've already drawn in the picture the forces, but let's talk about how I arrived at those. Now remember that the force on a charge, on a moving charge, or stream of charges, is the current times the length of the wire times the magnetic field times sine theta. But in this picture here, the currents, you look at the top current, the bottom current, those are 90 degrees, and so that just goes to 1. So we'll just say that force equals ILB. Now if you think about this bottom right here with the length of A, that means the force on it is I times A times B. Now the torque is going to be that force times the lever arm times the sine of theta. Now this is a different sine theta. This is the difference between, or this is the angle between the force and the lever arm. Now, if you think about what is the direction of the force, let's use the right-hand rule. On the bottom part, where my pointer is, use the right-hand rule, make your outstretched hand and fingers go in the direction of current, and rotate your arm so that your fingers point upward in the direction of the magnetic field, and you can see that it's forced outward. And if you go to the top and see the direction of force, well, current now is going to the right, so I'm going to take my right hand, point it to the right, fingers point upward, and my thumb points into the page. Now, on the left and right side, those don't have any effect. They're not affected by the magnetic field, I should say, because those currents are parallel or anti-parallel. There's an angle of 0 degrees or 180 degrees, and so there is no force on the left side and the right side. But we've established that there is a force. The bottom part is getting pulled out of the page. The top part is getting pushed into the page. So you can see that there would be this rotation. Now at the moment, let's look at torque equals, where my pointer is, torque equals force. We've established the direction and the magnitude of force times the lever arm. Now this thing is going to be rotated about an axis that's going through the middle. So right here. So the lever arm is actually half of little b. So little b over 2 is the lever arm. And at the moment, that angle, that sine theta, it's a 90-degree angle because the lever arm is going vertically and the force is out of the page, and so that's a 90-degree angle. Now once this thing starts rotating, it's not going to be 90 degrees, but at the moment it is. So let's compile all these torques. The sum of the torques, or the net torque, is the torque on the top plus the torque on the bottom. Now they're both in the same direction rotationally. They're both making it so that the bottom part gets pulled towards us and the top part gets pushed in, so the torque is in the same direction. And when we use our torque equations, we can say the force, which is IA times magnetic field, times the lever arm, which is little b over 2, and that torque is duplicated on the bottom. So together it's current times little a, little b, so length times width times the magnetic field. Now little a times little b, length times width, that's the area of the rectangle, so we'll call that big A. So the torque then is current times area times magnetic field. And now let's remember that for a current loop, current times area is mu, the magnetic dipole moment. So now let's include that once this thing starts rotating, torque is actually mu times b, but then there's that sine theta that I've been neglecting. So now we're looking from a different angle. Here's the magnetic field, here's the loop. We're looking at it edge on, and you see it's going to rotate. So you see it's getting pushed. Now, as soon as it starts to push, this angle theta is going to change. So it starts getting pushed, theta gets bigger. So the sine of theta is going to get smaller. And what we see is that through its motion, torque is the cross product of mu and b, the magnetic dipole moment and the magnetic field. Just as for the electric dipole, remember torque was the electric dipole moment times the electric field. So you see those similarities right there. Magnetic torque causes magnetic dipoles to align their magnetic moment vectors with magnetic field. And with that in mind, I want you to think about that wire loop that when put in a uniform magnetic field, it got rotated. And a wonderful application of that is an electric motor. An electric motor is something that turns electric energy into mechanical energy. From electricity, you can get motion. The idea behind an electric motor, you can see this wire loop that goes through that's going to have a current in it. We've got our uniform magnetic field, just like in the previous example that I was doing. And what's going to happen is that as the current goes through, it's going to get pushed around. And the thing is, if you trace this thing going around 180 degrees, it would have and the current stays going in the same direction, it would actually just oscillate back and forth. But what we've got here, I know maybe a little difficult to see, but you have these brushes that come in contact with the loop. So basically the current changes direction every time. And so basically the upshot of it is if every time it rotates 180 degrees, the current through the loop changes direction, then it'll keep on rotating in the same direction. Here we have a straight on look of, we have the North Pole, the South Pole, and so the magnetic field. And here is the loop. And right now, as I've drawn it, we've got the current at the bottom going out of the page, and at the top, the current going into the page. So at the moment, the magnetic dipole is facing in the direction that I've drawn it, down and to the left. And so the magnetic field will serve to align that magnetic dipole. Now, remember, torque is mu cross b. And so you think about the direction of torque. Just remember right-hand rule for cross products or for torque is going to be you're going to curl your right hand from mu into b. And here you can see that on this picture down here, it comes out of the page. Another application of this is at the atomic level. Think about that we found that the magnetic dipole moment is the current times area of the loop. That's measured in amperes times meters squared. And I want you to think about at the very tiny, the subatomic level, an electron orbiting a nucleus is a tiny current loop. It's one little charge that's moving around and around. It's a tiny current loop, so each atom has some magnetic moment. And therefore, atoms in magnetic fields experience torques. This is actually the cause of most magnetic properties that we observe in materials. I started out this chapter talking about that the cause of magnetism, the cause of magnetic fields, is moving charges. And I showed a picture of a horseshoe magnet and asked the rhetorical question, what do moving charges have to do with this horseshoe magnet? We're not running a current through it from a battery, but it's actually at the atomic level. So you have in magnetic materials, you have all these atoms that align in certain ways, so that every little atom with its little magnetic dipole moment, they align, and it gives magnetic properties to materials. To learn more about that, I encourage you to read section 26.7 in the book. It's only about a page and a half or so, particularly on ferromagnetism, paramagnetism, and diamagnetism, to read about how different materials exhibit magnetism in different ways. And that is the end of chapter 26. Have a great day.